All right, I'm back. Somehow my internet cut out. I had to reboot. Can you hear me?
Yeah.
Okay.
Yes.
All right. So when it cut out, what did you see on your screen? Did it go black or what happened?
Yeah, totally black.
Okay.
Mm-hmm.
All right. So I took this differential equation. I separated the variables. I brought the function of y from the right side to the left side of the equation. And I have this, which I have to integrate. If I multiply and divide by 2, then this I see is 1/2 the log of 1 plus y squared. And this is equal to log x plus 1/2 x squared plus a constant. So if I multiply through by 2, that makes it slightly nicer to look at. I get the log of 1 plus y squared is 2 log x plus x squared plus a constant. 2 log x is the same as the log of x squared. So if I exponentiate, I get 1 plus y squared is e to this, which is x squared, e to the x squared times e to some constant, which is just another constant. So the solution of this differential equation is defined implicitly in this way. Since I only have a y squared, I could actually solve that for y, but there's no reason to. But I've solved the differential equation. For any constant c, the function y squared defined implicitly by this equation is a solution of the ordinary differential equation I started with. Questions about this?
So the last technique I learned, we just apply for homogeneous.
Well, wait. What you just said was the last technique you learned. That means what you're saying is the last technique that we talked about in the course was homogeneous ordinary differential equations. Why would you think that has anything to do with this homework assignment?
Well,
if you look at the homework problem, it's first of all, it's in the section on separable equations. In any case, it's the equation is not homogeneous. So the right-hand side, when you solve for y as a function of x, this function of x and y is not homogeneous. If it's not homogeneous, you cannot use the technique for homogeneous equations. So you can try it and see if it works, and you immediately see that it doesn't work, and therefore you have to try something else. You know, if one thing doesn't work, try another thing. That's what you do in mathematics. Are there any other questions that I should go over?
Can you go over question 3 on page 333?
Let's take a look. So page 333, exercise 3. So this is to solve the differential equation y double prime plus y prime equals x squared plus 2x. And the special technique that works here is the following. If you have the second order equation with constant coefficients that is not homogeneous and the right-hand side is a polynomial, you try a solution which is a polynomial. If you have a y term, you look for a polynomial of the same degree. If you don't have a y term, but you have y prime, you look for a polynomial of one higher degree. So one higher degree than 2 is 3. So we would try a function y equals ax cubed plus bx squared plus cx plus d. Okay. So that's the first step. So do you understand why I wrote down a cubic polynomial and maybe not a quadratic polynomial?
Why the reason? I use the quadratic form.
Sorry?
I use the quadratic form because the higher exponent is 2. So what is the reason is 3?
But if you use a quadratic polynomial, it's not going to work. Right? I mean, you can try a quadratic, but it'll fail to solve the problem.
Okay. And the reason, what is the reason for that? Because,
Sorry, what is the reason?
yes, because.
All right, so the reason is if you start with a quadratic polynomial, if you differentiate it once, it becomes linear. If you differentiate it twice, it becomes constant. So on the left-hand side, you only get a polynomial of degree 1. There's no way to get a polynomial of degree 2. So it's impossible that there's a particular solution of this equation where y is a quadratic polynomial, because y isn't there. If you start with a quadratic, y prime will be linear and y double prime will be constant. So the sum will be linear, and a linear polynomial is not equal to a quadratic. But if you start with a cubic, when you differentiate it once, you get a square term, an x squared term, and there's a chance that it will work. I mean, that's the reason. And that's also, you know, if you read the book, that's what's explained in the text, right? So this is y. What is y prime? It's 3ax squared plus 2bx plus c. You differentiate the cubic, you get a quadratic. You differentiate again, a quadratic, when you differentiate it, gives you a linear polynomial, 6ax plus 2b. So if you take y double prime plus y prime, that's 6ax plus 2b, that's y double prime, plus y prime, 3ax squared plus 2bx plus c. When you add them, you get a quadratic, 3ax squared. I have 2b plus 6a times x, and 2b plus c. That's what I get. And I want that to be equal to x squared plus 2x. So I want to choose a, b, and c such that this equals x squared plus 2x. So the constant term is 0. The linear term, 2b plus 6a, is equal to 2. If you divide by 2, b plus 3a is equal to 1. And the coefficient of x squared, 3a, is equal to 1. So from this, we get that a has to be a third. From this, if b plus 3a is 1, b is 1 minus 3a, which is 1 minus 3 times a third, which is 1 minus 1 is 0. And C is equal to minus 2b, which is also 0. So we get a particular solution of the equation is y1 equals